let's talk about extreme values of functions. So, we can talk about the maximum of a function and the minimum of a function. So, let me just focus on maximum. Minimum is very similar. So, suppose f is a function defined on a subset of the real numbers and takes values in the real numbers. We say that a is a maximum of f if f of x is less than or equal to f of a for all x in I. So, this definition is relative to the domain I on which the function is defined. And similarly, you can define minimum by reversing the inequality here. If a is a minimum of f if f of x is greater than or equal to f of a for all x in I. And the value that f takes at the point a is called the maximum value. It seems like a very straightforward definition, but there are lots of strange things that can happen and sometimes wonderful things happen. So, let us look at a couple of examples. So, let us consider an example where something strange happens. Let us take I to be the set open interval 0 infinity. What this means is the set of real numbers x such that x is positive. And let us take f of x to be 1 over x. Now, if you draw the graph of this function, you will see that it is a hyperbola, something like this. And this function is always decreasing, and if you take any point, any positive real number x, you can find a real number that is positive and less than x, and there the value of the function will be greater. And if you take a point to the right, given any real number, positive real number x, you can find a real number to its right, and there the value will be less. So, this function does not have it has no maximum or minimum. Okay, this function in fact is not bounded above, so we cannot expect it to have a maximum, but it is bounded below, so we may have thought that it should have a minimum, but it does not. Here is another example which we can look at. Let us take I to be the entire real line, and let us take f of x to be 1 over 1 plus x squared. So, this denominator 1 plus x squared never really vanishes, and so this is a well defined function on the entire real line, and if you try to plot its graph, you will see that it looks something like this. This function is in fact it is bounded. It has a maximum at x equal to 0. Think about why this is the maximum, try to prove it, and it has no minimum. But one very surprising fact, or maybe once you get used to these things, it is no longer surprising, but it is surprising the first time you see it, is the following theorem, that if you have a continuous function on a closed interval, then it always has a maximum and a minimum. So, if f on a closed interval a b to r is a continuous function, then f has a maximum and a minimum. In particular, this means that such a function is going to be bounded. In the examples we saw just now, the interval that we looked at was not a closed interval. First we looked at positive real numbers, and then we looked at the entire real line. and that is why those functions fail to have maxima or minima. But this theorem tells us that if you have a continuous function on a closed interval, it must have a maximum and a minimum. So, the proof is in the same circle of ideas that we have with the Bolzano-Weierstrass theorem. In fact, it uses that. So, let's just go through the proof. It's not very difficult. So, firstly, we will show that the function f is bounded. So, first we show that f is bounded. Let us argue by contradiction, right. So, suppose f is not bounded, then this means that f attains arbitrarily large values on points between a and b. So, we can just pick points where the values of f keep growing larger and larger. So, for every natural number n, pick a point x n in a b, in the closed interval a b, for which f of x n is in absolute value strictly greater than n. So, this is a sequence of points where the value of the function keeps growing and growing and growing. And what do we know about sequences in a closed interval? Well, they have convergent subsequences. So, let x I k be a convergent subsequence of x n. So, this sequence is convergent, it must have a limit. Let x 0 be the limit as k goes to infinity of x I k. So, now this point x 0 will lie in the interval a b, and what can we say about the value of the function at x 0? Well, the function has to be continuous at x 0. So, note that f is continuous at x 0, which means that for every epsilon greater than 0, there exists delta greater than 0, such that if a point x is within a distance delta from x 0, then f of x 0 minus f of x will be less than epsilon. So, let us just take epsilon equal to 1. So, by continuity what we have is f of x minus f of x 0 is less than 1 for all x. So, by continuity we say that there exists delta greater than 0 such that f of x minus f of x 0 less than 1 for all x such that the distance between x and x 0 is less than delta. Now this sequence x I k converges to x 0. So, there exists a natural number n such that if k is greater than n, we have x I k minus x 0 is less than this number delta that we have. So, now we have f of x I k minus f of x 0. Well, this should be less than 1, right, because x I k is close to x 0. So, f of x I k minus f of x 0, well, by the reverse version of triangle inequality, this is greater than or equal to f of x I k minus absolute value of f of x 0, right. But f of x I k is greater than, so x, remember we had chosen x n such that absolute value of f of x n is greater than n. So, f of x I k is greater than I k. And minus f of x 0. Since this holds for every k greater than n, I can also choose ik is so large that ik is greater than f of x naught plus 1. Okay, this is a finite quantity. So, by the Archimedean axiom for natural numbers, I can do this. And so, what would that mean? That would mean that this ik minus f of x naught is greater than 1. So, f of x ik minus f of x naught is greater than ik minus f of x naught, but that is greater than 1, which is a contradiction to our choice of delta. So, this shows that the function f has to be bounded, and now let us show that it has a maximum. Since f is bounded, we can define we can take the supremum of its values. And I will show that this is the maximum value in fact. So, now what you do is, since this is the supremum, if I look at any number smaller than this, so if I look at capital M minus 1 over n for any natural number n, I can find a point in the interval a b such that f of x n is greater than m minus 1 over n. So, what I can do is, for every n in n, I can choose x n in the closed interval a b such that f of x n is greater than m minus 1 over n. And again this sequence x n in a b has a convergent subsequence. So, let x I k be a convergent subsequence. And as before, let x 0 be the limit as k goes to infinity of x of I k. Then what we have is, for every epsilon greater than 0, because of continuity of f at x 0, there exists delta greater than 0 such that if x minus x naught is less than delta, then f of x minus f of x naught is less than epsilon. And now you choose k large enough, choose capital N such that if k is greater than n, then x I k minus x is less than delta. So, now we have absolute value of m minus f of x naught. This is equal to m minus f of x I k plus f of x I k minus f of x naught. And so, now using the triangle inequality, this is less than or equal to m minus f of x I k plus f of x I k minus f of x naught. And m minus f of x I k, well, that is going to be, so let us look at this. M is anyway an upper bound for the values of f on the interval a b. So, m minus x I k is certainly positive, and we also have this condition that f of x n is greater than m minus 1 over n. So, f of x I k is greater than m minus 1 over I k. So, what we get here is that this is less than 1 over I k plus and f of, so now remember x I k is within a region of within a distance delta from x 0, this should have been x 0, and so f of x I k minus f of x naught is less than epsilon. So, now if I make sure that I also choose I k such that 1 over I k is less than epsilon, then I have m minus f of x naught is less than 2 epsilon, and this is true for every epsilon positive. So, this implies, as we have seen before, that f of x naught is actually equal to m. Now, a similar argument can be used to show that a function, a continuous function on a closed interval has a minimum. If you do not want to repeat the argument, you can just take the function f and replace it by minus f. Minus f will have a maximum, and then a maximum for minus f will be a minimum for f. And so, a continuous function on a closed interval has both a maximum and a minimum.